Hi everyone, my name is Duncan and I will be presenting the demonstration of the Graph-Massivizer tool. This demonstration will consist of three parts. First, an end-to-end demonstration of the tool, showing how it can be used in practice. Then we go a bit deeper into the inner workings of the tool and how the prediction is done. And finally we show how Graph-Optimizer can be used to automatically generate optimal CPU and GPU code. So for the end-to-end pipeline, Graph-Optimizer takes three inputs. The workflow as specified by the user, the hardware on which the workflow will be run, and the properties of the graph to which the workflow will be applied. We then take these inputs and apply our prediction models to predict the runtime, the energy, and we generate optimal code. We will use the following workflow throughout this demonstration, where the arrows indicate dependencies. So we start with PageRank, after which the BFS and FindMax BGOs can run, and the outputs of BFS and FindMax will be used to find the shortest path from the source of the graph to the node with the highest PageRank in the FindPath BGO. So this is how it can be used in practice. We have the Graph-Optimizer end-to-end function, which takes three arguments: the workflow, the hardware, and the graph properties. We also see two other optional arguments here. Targets, which specifies what you want to optimize. So since Graph-Optimizer can optimize for both runtime and energy. And the correction is a fine-tuning parameter. And this depends on the input graph, and we will explain later why this is necessary and how it is used. So as you can see, Graph-Optimizer is busy predicting the runtime for all implementations for the BGOs from the workflow. So both CPU and GPU. And this will take a few minutes. So for each BGO, for all the implementation, there will be a runtime prediction and an energy prediction. And the best implementation will be selected. So after about 2 minutes, the predictions are in, and the optimal BGO for each the optimal implementation for each BGO has been selected. And we can now use this output to automatically generate an end-to-end implementation of this workflow in C++. So since I run this on a single machine with only one CPU and one GPU, BFS and FindMax cannot be executed in parallel. So an execution plan is made where all the BGOs are executed sequentially. So the code is generated, we can compile and run it. And as you can see, the workflow took about 13.8 seconds and took a little over 475 megajoules of energy. Now let's see how this compares to our prediction. So here we see two plots, one for the runtime and one for the energy, and each of them has two bars. On the left hand side we see the prediction, and on the right hand side we see the measured time and energy. So for the runtime we have an error of about 13%, and for the energy only about 2.5%. But how much time and energy did we save by using Graph-Optimizer? Well, we can use the same techniques to select the worst performing implementation for each BGO. And this will take a while. So the results are in, and we see here that in the worst case, the runtime and energy can be almost 2 orders of magnitude higher than in the optimal case. And this is very dependent on the specific graph at hand. So for some graph structures, these might actually be the best case. The inputs for Graph-Optimizer are mostly automatically obtained, except for the specification of the workflow, which the user can define in JSON format as follows. Each BGO has a unique ID, and the dependency arrows can be specified in lists for each BGO. The hardware information of the CPU and GPU is automatically extracted, and micro benchmarks are also automatically executed. These micro benchmarks are used to calibrate the analytical performance models, which we will see in a minute. And finally, the graph properties can also be automatically extracted from the graph. So these can be the number of nodes, number of edges, and some relevant statistics for our models. To select the optimal implementation for each BGO, we use two different performance modeling techniques. First is analytical models. The benefit of these is that prediction is instant and they can be very portable across different hardware setups. However, they are also notoriously hard to achieve high accuracy with, especially for graph processing and even more so for the GPU. This makes them infeasible for a lot of the BGO implementations we have. In this plot we see the predicted execution times and energy consumptions using these analytical models for some of the BGO implementations. Each BGO has CPU and GPU implementations, but we only have analytical models for the CPU implementations. So we designed a new method, which was published in Graph-Sys 2025, which uses a small sample of the graph to execute the BGO implementation in a fraction of the time. We can then use this millibenchmark to give a much more accurate prediction of the execution time and energy consumption. However, to get the most accurate result, there has to be a human in the loop to fine-tune the model for the specific type of graph. This only has to be done once for each use case though. We use these to complement the analytical models, and we see here the predicted execution time or energy consumption for all implementations. From these, for each BGO, we take the implementation with the lowest runtime or energy consumption, CPU or GPU. Next up, the automatic code generation. For this, the workflow has to be annotated with the data flow between BGOs, as demonstrated in this diagram. If Graph-Optimizer is used within the Graph-Massivizer ecosystem, this can be automatically done, but if used as a standalone tool, the user has to annotate the workflow with these data flows. And this is done as follows. For each BGO, there is a list containing mappings between the output parameter of one BGO and the input parameters of the other. Then, when running the end-to-end prediction, Graph-Optimizer will annotate the optimal implementations in this workflow, along with the predictions of runtime and energy consumption, which are the implementations that are used for the code generation. So here we see the generated code with all the BGO parameters and the function calls with the input and output parameters. Finally, with a small conversion, this output can be directly used as input for the Graph Greenifier tool, which uses the runtime and energy predictions in the OpenDC simulations, which you will see in a later demonstration. Thank you.